This idea of undergrad is being the influence law, but the pool is very kind of the education I think.
You recognize we just did an icon.
One more thing. 6 plus 1. You just don't have a name. It's subsided.
Somebody has one name, I have no name. Awesome.
Is it allowed these days?
Exactly. I did not do I did not start doing anything during COVID. I did for so I started the idea.
So what is people should come back?
So it's that.
Okay, why don't we start while the bus comes? So welcome to CODS-COMAD 2023. This is the 10th CODS, the 28th COMAD, the 6th joint one. I've already attended 2, so this is my 3rd CODS-COMAD. It was COMAD before. I am one of the 2 general co-chairs for this conference, Amr El Abadi, and we had a recursion problem. Who introduces who? So somehow we have to do it. So I'm going to introduce Pushpak, and then he'll introduce me, I guess. Pushpak is a professor of computer science and engineering here at IIT Bombay. He's an expert in machine learning and NLP. He's a fellow of the National Academy of Engineers, Abdul Kalam National Fellow. And by the way, I attended a talk by Abdul Kalam, I think it was 2014 in Dub. He was an amazing speaker. And he's a former president of the Association of Computational Linguistics. So please welcome Pushpak.
So welcome to all of you to CODS-COMAD 2023. And as is the practice, many places, we seek the blessings of the Lord before starting the proceedings of the event. So I'm going to sing for you for 1 minute an invocation which is from Shweta Upanishad, and this is one of the epitomes of the philosophical knowledge of India. So it goes like this. Shrinantu Vishwe Amritasya Putra Dhamani Divyani Tastu Vedahamitam Purusham Mahatam Aditya Varnam Tamasa Parastat Tameva Viditva Mritum Yeti Nanyapantha Vidyate Yayanaya Nanyapantha Vidyate Yayanaya. Meaning, listen, O world, O children of immortal bliss, all of you who are on earth and on the heavenly bodies above. I know the great being, like the effulgent sun, beyond darkness. Only by knowing whom one passes the darkness, there is no other way. At the outset, it is my pleasure and honor to invite our Deputy Director, Professor S. Sudarshan, who is a Professor of Computer Science and Engineering in IIT Bombay. He is a Fellow of ACM, Fellow of IEEE, and Fellow of all academies of India. He has made immense contribution to databases. Professor Sudarshan, please.
Thank you, Professor Pushpak. It gives me great pleasure to welcome all of you. Although I'm an insider to this conference, having helped organize this and been on the steering committee, today I will wear a different hat also as Deputy Director of IIT Bombay to welcome all of you to the campus. But of course, first, welcome to the conference itself, to the campus. This is the first time we are having CODS-COMAD here. But many years back, 2008, we had COMAD here. And IIT Bombay also has a lot of people working in the area of data science. And we have had actually a significant increase in the number of people working in this area. So this was a great year to bring CODS-COMAD back here. It's also great to see CODS-COMAD back in physical form. Bangalore tried hard. First time it became virtual. Second time they tried again for hybrid. Again, it became virtual, but we are lucky to have come out of that and actually meet physically. It's really nice meeting people. The kind of interactions which you will have with other people at the conference, in the corridors, over dinner, is something which just cannot happen in virtual mode. So it is really nice that we are back physically, and I hope all of you enjoy the conference. In addition, while you're here, please do enjoy the campus itself. If there is a lake, in fact, there are two lakes. One is out of bounds, one is accessible. We have a couple of hills, one again out of bounds, but one accessible. So if you have time, not during the sessions, please, but outside, do feel free to walk around campus, walk by the lake. There is a boathouse, if you can find the way to it. There are a lot of birds also there. So do stop by there. Mornings and evenings are great times to go there. Now, coming to IIT Bombay's data science initiatives, we have long had a number of people in the computer science department working in this area. But a few years back, we realized that data science is actually much bigger than computer science. It encompasses every department. And as a result, we started a new Center for Machine Intelligence and Data Science, which of course came from the nice acronym C-MINDS, very appropriate. And now we have a large number of students who are now joining it at the master's level and also doing minors and so on. And we are also actively recruiting faculty. So some of you who are graduating, please consider joining us. And this center has also got a lot of donations for labs and actual building, which is coming up. So in a few years, that should be up. Now, some of you students are staying out of campus because we couldn't offer you accommodation on campus. We are kind of stretched for housing here, but we also have a big construction boom. So next time CODS-COMAD comes here, I hope that everybody will be able, we can accommodate everyone on campus itself. So with that, I'll stop and wish CODS-COMAD and all of you a very successful conference. Thank you.
Again, it is my pleasure and honor to invite Professor Amra El Abadi, who is a professor of computer science and engineering at University of Santa Barbara. He is fellow of ACM, IEEE, and AAAS. He has made immense contributions to distributed databases.
So good morning again. So the registration seems to be hovering around 400 attendees. We are supposed to have 250 in person. I don't know if everybody's here or not. This is the first in-person hybrid conference since the pandemic, so this is very exciting. And as already Sudarshan said, it's really a great opportunity to interact and talk. Please, especially the students, don't hesitate to come and talk to me, to anybody, and just chat about various things. The conference is quite busy. We have 6 keynotes. We have tracks for 2 different sets of papers, the research, which has 18 papers, 12 long and 6 short. We have the applied data science, which has 16 papers, 7 long and 9 short. We have 5 demos. There's a young researchers symposium that's going to take place today and tomorrow. We have a very extensive diversity, inclusion, and equity program. We have a speaker, Anjana Susrala, who's going to talk, I think, tomorrow. There's going to be a panel. There are experience talks. Yesterday, there was a workshop on inclusive design, and I attended the last part of it, and it really sounded exciting and interesting with innovative ideas. There's an IKDD tutorial dissertation award, and that will take place on the last day, Saturday. We have 12 posters that will be during the conference taking place. Yesterday, we had several tutorials, and I think they were very good. At least the one I attended, I enjoyed very much. We have sister conferences talks, which are 3 talks from various international renowned conferences that were selected to be presented here to you. In terms of social activities, there's a banquet, there's a reception. I especially encourage you to attend the keynotes. They are very diverse in flavor. We have various speakers. Sriram, who's from Microsoft Research, he's going to be talking about AI-assisted programming, something of great interest. There's Maria Esther Vidal, who's going to talk about graphs and biomedicine. There is I told you already about Anjana, and then who's going to talk about patient education needs on social media. We have Angela Bonafatti, who's going to talk about graphs. Arun, who's going to talk about databases and its relationship with AI and machine learning. And last but not least, Mausam, who's going to be talking today, just after I'm done, about reasoning and perception. So there are lots of exciting things. And just as a parting words this is a very exciting time. And I have to say that being a database systems researcher, I find this one of the most fulfilling endeavors. And I know there's a lot of interest and great work that is happening in the various fields of computer science. But from a very data-centric point of view, I would argue that all the innovation that is happening, whether it's in machine learning, natural language processing, all my colleagues here, they need a lot of data. Managing this data is critical. Providing it is critical. Maintaining its privacy, distributing it, etc. All of these things are critical. So let me make a pitch for this is a great field which encompasses much of what is great about computer science. And it's an opportunity for us here to appreciate this in this conference from technical point of view and for the future. So I'll stop here and I'll give it back to Pushpa. Thank you.
Now we come to 4 very eminent researchers who actually take care of the heart of this conference. So we have with us Professor Luika Rashid and Dr. Pranit Netrapalli, program chairs for the research track of the conference. Professor Luika Rashid is professor of Robert H. Smith School of Business and UMIACS at University of Maryland. ACM and IEEE fellow, Professor Rashid has made immense contributions to data management and data science in medicine, finance, socioeconomics, and so on. Dr. Netrapalli is a research scientist at Google Research, Bangalore. He is also adjunct professor of TIFR. He is an alumnus of IIT Bombay, and he makes foundational contributions to reliable and robust machine learning. Professor Luika Rashid, please.
Thank you. In the interest of time, I will keep it very short and just say that managing the technical research track was a great pleasure. And one of the innovative things that we did this year was to give a lot of feedback to the researchers. We had a 2-phase version of asking people, first review cycle, giving feedback, and then hopefully the papers improving. And one of the interesting things that happened was that the papers improved so much that some of them were actually nominated as best paper at the end of the conference. So I think listening to the feedback from the reviewers is usually a very good thing. So I'll end there. Thank you very much.
Professor Pannurangam Kumaraguru, who is very fondly called PK by our community. He is a professor of IIIT Hyderabad. After his PhD in Carnegie Mellon University, he was for some years in IIIT Delhi, and he works deeply on research questions in social network analysis. The co-PC chair for Applied Data Science track is Dr. Tanuja Ganu. She is a research SDE manager at Microsoft Research India and is part of a new center of social impact through cloud and AIs called Sky. After her PhD in IISc, she was in IBM for some time. May I invite Professor Pannurangam Kumaraguru to say a few words.
Good morning, everyone. Good morning. No. Good morning. Last time. Good morning. Okay. How's the Josh? I'm hearing only from this side. Josh is not that very high this side, I guess. So let me give you some details about the ADS track. Tanuja and I spent some time on reviewing. Totally, we had 56 papers reviewed, submitted. We had 47 reviewers. We had sub-reviewers, so 14. Number of papers accepted in the round 1 was 9. We also did the R&R, but we added one more layer to the R&R was we had an open house where Tanuja and I were on the call, where we asked all the authors to show up on the call if they wanted feedback. Actually, at least one author from all the papers that were accepted in R&R showed up. How many of you joined the call in R&R open house? How many of you submitted paper in ADS? How many of you are presenting? Okay, good. So the number of reviews on average a paper must have gotten is 4, minimum was 3, maximum was 6. Total number of paper accepted is 16, 7 full paper and 9 short paper. So for people who are presenting, please show up in the, I'm sure this may have been given otherwise. I thought I'll make use of this opportunity to tell you, please show up in your session 15 minutes before so we can actually set up all your slides and everything, okay? And I will do my selfie also. Okay, so I'll do one this side and one this side. I'm not doing that side. So. Okay. If any of you want this picture, please take it from my social media. Thank you.
Now, we have a very important person amidst us, Dr. Shaurya Roy, who is the president of IKDD, ACM Sikh KDD India, under whose umbrella this event is taking place. Shaurya is Senior Research Director at Flipkart. He is an alumnus of IIT Bombay. He has over 2 decades of experience in leading data science in IBM, Xerox, American Express, and Flipkart. Shaurya, please.
You feel embarrassed when the person who had taught you NLP at the first place calls you an important person. Thank you, sir. Okay, welcome everybody. It's a great pleasure to welcome all of you to the CODS-COMAD 2023, which is the 6th joint edition of the conference in this wonderful campus of IIT Bombay. I congratulate and thank the general chairs of the conference and all the other track chairs for putting together a very, very exciting agenda. And we're looking forward to an excellent conference over the next 3 days, which has already started. Yesterday was the first day in the next 3 days as well. I thought that I'll spend like 2-3 minutes, I know we are short on time, to tell the young students especially how these 2 conferences actually came together. I don't know if many of you would know that COMAD of course, from the number of years it has been existence, but COMAD has been a very, very significant conference in the databases and data management for close to 30 years now, right? In fact, not only in India, COMAD is one of the well-known and recognized conference in the internationally as well. And in the early, we used to get like a lot of papers from the external other countries and so on and so forth. In fact, when I was student, COMAD, we used to look up to COMAD as a very, very prestigious conference. About 10 years ago in 2014, after IKDD was formed in 2012, we started this conference with data science focus called CODS. And of course, it was kind of with the rising popularity and of the data science as a domain, it was gaining high popularity. And then we realized over the next 2-3 years, there is a lot of synergy between the databases community of COMAD and the data science community of CODS. And then we started saying that, okay, let's do the usual thing when related conferences do is they start by doing co-location, right? So 2016 was the first year when these two conferences were co-located at, if I'm not mistaken, in Pune, when 1 day of Common Day was there and the 2 days of COMAD and 2 days of CODS were there. Then 2017, these two things came a little bit more closer, and they said that, okay, we'll have like 2 days of Common Day and 1 day of separate CODS and COMAD in IIT Madras. And 2018, we said, oh, enough of coming closer, let's get married. And in 2018, we got married in Goa, and these two conferences were born in as a joint conference, and that was the first year of the joint conference. So since then, I believe this is the most prestigious scientific conference on all things data in India. And of course, we do get a lot of interest and significant personalities like Loika, Amar from the international community coming and helping us growing this conference even bigger. And we look forward to this conference becoming even more significant in the coming years. Thank you very much, everyone.
Next. Okay, in the interest of time, maybe I will not go through the names of all our sponsors, but their immense importance, in making this event possible cannot be undermined. So we have been very lucky to have sponsorship from very leading industries, and their names are all displayed here. We would like to very gratefully acknowledge their help. Now it is time for the technical part of the event to start. And it is my great pleasure and privilege to introduce our inaugural keynote speaker, Professor Mausam from IIT Delhi. Professor Mausam is an AAAI senior member. He is also the founding head of ERD School of AI at IIT Delhi. Professor Mausam is not new to CODS-COMAD. He was PC chair a few years back. Professor Mausam is also an affiliate professor of University of Washington at Seattle. He has 20 years of research experience on large-scale information extraction, probabilistic planning, and artificial intelligence. More recently, his contribution to NLP and NLP for robots has been very noteworthy. He has over 100 archival papers, a book, 1 Test of Time award, 2 Best Paper awards. Arnett Minor ranks him as the 56th most influential NLP scholar and 64th most influential AI scholar. We are indeed very privileged to have Professor Mausam. Over to you.
It's okay, I can manage from here. Thank you, Professor Pushpak, thank you for such a gracious introduction. It's an honor to be here and talking to all of you about some of the recent work that we have been doing at IIT Delhi. Before I get started, I should also say, and I should also mimic Professor Sudarshan's initial remarks that machine intelligence and data science are slowly becoming bigger than computer science, bigger than some of the original AI fields. And as great minds think alike, IIT Delhi is also following suit and we have started Yardi School of AI, of which I am the head. We have some flyers. We are also hiring. We have already started the MTech program, PhD programs, etc. Talk to me if you're interested about that. Then let me also introduce this work that I'm going to present. But before I do that, I should mention that as Pushpak said, I'm somewhat also known for the NLP work that I do. But Pushpak specifically wanted me to talk about this work. So I'm happy to present this. But this is work primarily led by, with me, Professor Parag Singla has been sort of a partner in crime at IIT Delhi. He brings the technical smarts and he has been sort of a leader in symbolic representations. And as neural models have been taking over, we are constantly thinking about what's the relevance of the older style computer science, older style AI in the context of modern AI world. And so some of this work came as a consequence of those deliberations. I would mention that of course, as we get older, we don't do any work ourselves. So this is really the work of two of our PhD students, Yatin Nandwani and Vishal Sharma. Yatin has just joined IBM Research and Vishal is looking for a postdoc position. So if you're interested, you should talk to him. And we have been supported by lots of undergraduate students, master students, and other faculty colleagues whose work I'll be sort of bringing in as and when appropriate. So let's get started. We are anyway a little bit behind, so I'll try to cover a little bit of time in the talk. And let's start with something that we all know and understand, right? We all today are in the field of AI, often primarily because AI is suddenly becoming like doable. If you were 10 years ago a researcher, 15 years ago a researcher, you would not have believed that AI would have this kind of an impact today, right? So the kind of impact that we have had is just mind-boggling, and a lot of that has been led by the success of neural models. And there are some very key strengths of neural models that allow AI to be that successful, right? What are the typical strengths? One typical strength is that it's a universal approximator. It can learn really non-trivial functions. Earlier, we used to work in the world of linear basis functions and so on and so forth. This really goes beyond that. Also, it has compositionality built in. So some of the ways we think as humans, the way our brain works, they are very interesting analogs. The other thing that I think has been super amazing, I mean, again, going back 10 years ago, if you had told me that someday we will be able to take an image and write a caption from it, or take a textual description and create an image from it, I would have called it science fiction, right? Just 10 years ago. I'm not even talking, even when neural models had just started coming, right? So it's a universal representation across modality. It sort of brings various modalities together. Now you can work with video, audio, text, images, biology, everything in sort of one representation, which enables amazing synergies. And last but not the least, at least in the early days, this was very important, that often in the field of machine learning, features were provided by humans and machines' job was to optimize the weights for those features. This is what we all learned machine learning as, and this is what we were teaching our students. And suddenly that paradigm changed, and we said, oh, we don't need humans to give features. Generally, the features would be discovered automatically by the model, sometimes in a task-specific manner, so we are no longer limited by human creativity. So there are just so many strengths that neural models brought in, changed the paradigm, and now we are here where we are. We all understand and appreciate it, right? No big deal, today at least. In parallel, we have 60, 70 years of history in symbolic AI, right? And symbolic AI methods are built on high-level symbolic representations. There are symbols for concepts. There are expressions. You can combine symbols using and, or, not, various other operators to create new sentences. And you can then manipulate these expressions one way or the other. You can do inference on top of it, and you can ask interesting questions. People have done this in the context of formal logic, first-order logic, mathematical logic, various kinds of algebra, graph theory, and more of that. We have a lot of history in symbolic AI. And it is worth asking the question, should we just get rid of it today? Is it relevant anymore, or is it all going to be neural AI going forward? And I think that's a question we all grappled with when the deep learning world started, right? And some of the younger folks would be like, who cares for symbolic AI? Because as it often happens, whatever is the leading technology, the students will learn that and not worry about the others. But as we gray-haired people who learned some technology when it was important, we often enable ourselves to ask the question, well, what is the synergy? What is the relevance? What part of the old is still relevant? What part of history is still meaningful? And here is my incomplete comparison. And as you start thinking about this, you can also start to see some points that I have not mentioned. But let's think about this, right? So, for example, neural AI is generally annotated data hungry, right? You need a huge amount of labeled data to get the neural AI to work. But that's not surprising. These are universal approximators. Therefore, the models have low bias, so they are high variance, so you actually need too much data to get them to work. Symbolic AI, on the other hand, often can be model-based. So the human provides the model, and once the model is provided, you may not even need any data, or the model gives a very strong bias, and you need only a smaller amount of data to train the parameters. Because of that, neural AI is compute hungry at train time. On the other hand, symbolic AI, as we discussed, does not require much data and computation. Now, this often gets flipped at test time, because at test time, neural models are just one forward pass typically. Again, these are some high-level approximations. You will find that in some specific examples, this may not hold, but these are broad strokes. So you will find that neural AI will sort of do one quick forward pass, and so it will give you an answer pretty quickly. On the other hand, symbolic AI may sometimes require you to learn to run a complicated inference procedure, right? And those inference procedures can sometimes take a lot of time. So they may sometimes require more computed testing. Neural AI is still not reaching a place where it can give you guarantees on output. So if we are in a safety critical situation, if we are figuring out where to put the injection in a patient, or it's a multi-billion-dollar satellite that is going into the into the space, we may not want to just rely on neural models. Symbolic AI has been known to prove things for us and can give us guarantees on one way or the other. Similarly, neural AI is highly uninterpretable. We can scratch our head, we can bang our head at the wall to figure out why neural AI is not working, or why neural AI is working in the first place. Nobody knows. There are many interesting XKCD comics on, we don't know why neural AI works or doesn't work, and therefore it becomes harder and harder to debug. And most of the time, our students are just playing with hyperparameters, amount of compute, blah, blah, blah. And suddenly they'll say, oh, we got the result. And, is it good result? Is it the right result? Will it be replicated? We don't know. So there is a lot of uninterpretability in the neural world. In the symbolic world, obviously, we understand what's going on. We understand the algorithms. There we have much more control. And from a more application point of view, at least this is my view, that neural AI, it is kind of, now nobody's going to question it, undeniable, that it is amazing at perception. The kind of uncertainty, the kind of model uncertainty, environmental uncertainty that the neural AI is capable of handling, which is needed for perception, is unmatched by symbolic. But on the other hand, when it comes to reasoning, when it comes to thinking about what we know and drawing inferences and so on and so forth, that's where I think symbolic AI still has strength. And as a case in point, you take all these SAT solvers that we have been developing for the last 15 years, and you try to solve the same SAT problems using a neural model. We are at least a decade away from it. At least this is my prediction. I will be wrong, proven wrong in 2 years. Who knows, right? Something else comes up. So this is sort of my caricature of what neural AI gives us and doesn't give us, and what symbolic AI sometimes gives us in contrast to that. And so it goes without saying that if we do this kind of analysis, it makes sense to think about what are interesting synergies between neural and the symbolic worlds. Can we bring them together? And if we can bring them together, how will we bring them together and to what end? Right? So we want to combine benefits of neural and symbolic AI. And we can start asking the question, what can be symbolic inside neural? What can be neural inside symbolic? How do they interact? How do they come together? I would say that people have even said that if you give text as input or text as output, that's symbolic. And they're not wrong. But to me, that's degenerate form of symbolic. So I will go out and say, okay, we are not talking about the simple interplays where one of the inputs or one of the outputs are symbolic. Let's not worry about that simple paradigm. But I am more interested in thinking about whether interesting symbolic representations or interesting symbolic algorithms come in context of neural AI. So that's where I'm going to focus most of this talk on. So what can be symbolic inside of neural AI? Well, constraints could be provided by humans, some domain theory, some model of the world could be provided by the human, some intermediate symbolic representation may be induced by the model, some symbolic algorithm may work in conjunction with the neural. What can be neural inside symbolic? You may remember AlphaGo and so on. You have a symbolic algorithm running, and in the middle, the search is managed by the neural model, or some heuristics are computed by the neural model. So you can now start to think about various different ways in which these two fields come together. And I should mention that, I am not the main key initiator of this kind of an agenda. I believe that the first time I heard this in sort of a major stage was in 2018 at an IJCAI award talk by Professor Henry Kautz, who sort of delineated various ways in which neural and symbolic comes together. And later, more and more people started to pursue this agenda, to the extent that when we did AAAI 2021, neural symbolic AI became one of the focus areas of the whole conference. And so in the field of AI now, in the last 4 or 5 years, there is a lot of energy in this field. And what I'm going to do today in this talk is going to share about some of the various ways in which we have combined them. And in this slide, I give you like a summary of what we have done in our group. And on the right, I show you why we have done it. Okay. So we have thought about features. I told you that neural AI can discover features automatically, but it's not always complete. There are more features that humans can come up with, while neural AI can come up with features which are not limited by human creativity. Human creativity sometimes is not limited by the creativity of neural models, right? So as in the world, I'll just give you like one bit of example. In 96, Deep Blue defeated Garry Kasparov. In 99, 2000, people stopped playing and competing against chess programs because chess programs were really, really better. There was no point in having a human play a program. That's true today. But do you know who's the best chess player? It's not a human and it's not a program. It's the combination of humans and machines. So as we evolve, as AI becomes better, as AI reaches superhuman abilities or human abilities, you will realize time and again that AI has an approach of looking at the problem different from that of a human. And when human creativity and AI creativity come together, it will become bigger than the sum of parts. And so in the same vein, if you have interesting features that are relevant for your problem, or some interesting constraints that are relevant for your problem, you should give it to the neural model and allow the neural model to benefit from them, right? And so that we have shown. And so this allows the human designer to give human domain insight. It gives us a knob to work with the neural model. It leads to better learning. It sometimes can lead to guarantees also, as we'll see. In some other works, we have gotten the neural model to output a symbolic program. And again, that there is going to be some talk by Dr. Rajamani on AI-mediated programming. And in the programming can come in different forms. So I'll today show you one example where AI outputs a sort of a program of a certain type, right? And that gives us a better interpretability on what is happening in my model. And we will see that it also allows for excellent scalability. Whenever we have to communicate to a human, we have to communicate in words or in symbolic representation. So in such situations where we have to deal with explainability, the neural AI generally outputs a symbolic explanation. So that is something we have worked on. Sometimes we have to bring in knowledge, and knowledge is stored in a knowledge repository. And it's a matter of philosophical debate whether knowledge should be part of the parameters of the model or separate. But in the cases it is separate from the neural model, the neural model has to query the knowledge engine, get the knowledge back, and then use that knowledge in giving the output. And in all such situations, the model becomes neural, symbolic, and maybe neural back. And in such situations, again, you have to bring in neural symbolic methods. Then we have worked on situations where there is a symbolic theory in the first place, but that symbolic theory is then taken up by the neural model to achieve the desired output. The symbolic theory may be complete, it may be incomplete, and again, we have worked on these situations. So I will give you some examples today. In the rest of the talk, I'm going to touch on 3 main topics as marked. And you can start to see that, and this is just a flavor of the work that we have been doing. And you can then, go back and brainstorm with yourself and with your friends, and you realize that you will find some very interesting synergies which have potentially been lesser explored, and it becomes a very exciting area of research today. Okay, so let's get started, and we're going to start with something relatively simple. When you have some additional constraints, how can a neural model deal with them? Okay. This, to me, is the most application relevant part of my talk, this particular first piece, because we have found it to be relevant in many applications ourselves. And just to get started, this is our standard training test paradigm in the neural world. You are given a data, you are given a neural architecture by a human, and you have a trainer like backpropagation, and it creates a trained neural model at training time. And at test time, what happens is that you have the input, you apply it on the trained neural model. Remember, it never outputs outputs. It outputs probabilities on the output, if it's a classification problem, for example. So it will give you output probabilities. You typically do an argmax, and that's when you get an output. So that's the standard training test paradigm in machine learning today. Okay. So if you have been lost, this is the time you all come in, because this is sort of standard stuff, right? At this point. Now, suppose you had some additional constraints about your outputs. Let's say, you know that my outputs should honor this constraint, whatever, some constraint. What do you do? Right? So one option is that instead of argmax inference, you do, first of all, you have to realize that if you have constraints, standard data trained neural model may not satisfy these constraints, right? So you want to impose these constraints. If you want to impose these constraints, the easy way is to impose them at inference time. So you have trained the neural model with complete disregard to the constraints, but then when you actually run it at test time, once you get the output probabilities, instead of doing an argmax inference, you do a constrained inference. So you figure out what assignment to my output variables will honor the constraints and would also be, a high probability output as far as the neural model is concerned. This is possible. We will call it constrained inference. But there is an alternative paradigm, which is, why not I train the neural model with the constraints in mind? And this is what I'm going to call constrained learning. Okay. So in this training paradigm, now the trainer will get access to the constraints. Okay. And then at test time, what happens? At test time, I will still do argmax. Why? Because now I have already imposed these constraints onto the model one way or the other. I will want to believe that my model knows the constraints, has learned to honor the constraints. And so test time, I can simply do argmax. I can also do constraint inference. Nobody's stopping me. But if we have done a training well enough, then we may not need to. This is the paradigm that we developed. And just to bring home this, make it concrete, let me give you some examples. So what kind of constraints could we have? So suppose I am predicting lots of labels, whether an entity is a scientist, whether an entity is a person, whether an entity is a vehicle. Then I have very simple constraints like, if you are a scientist, you are also a person. Don't make a prediction where you say somebody is a scientist but not a person. But if somebody is a scientist, most likely they are not a vehicle. So, don't make these nonsensical prediction that this entity is a scientist and a vehicle, right? So you can actually list these constraints, and it's going to be very easy for a human designer to list these kinds of constraints, right? If I'm working in, let's say, named entity recognition part of speech tagging tasks like multitask learning, you can have constraints like, if you're a person in NER, then you are a proper noun in part of speech. Or if you're an organization in NER, then you have a certain part of speech. Or if you're a time as an NER, then there are certain types, a certain part of speeches that make sense, right? So you can actually list these constraints as a human designer, as a linguist, and then you can see how these constraints can be honored by my neural model. And again, you will start to see that these kind of constraints will show up, and I'll give you some other examples towards the end of this part. Now, let's work with this. So let's say we work on person implies proper noun. Notice that my neural model does not output whether an entity is a person. It only outputs the probability that an entity is a person or a word is a person. Right? So we are given probability of a person, probability of a neural model, which is something that is outputted by the neural model. So we can convert this implication into a statement over the probability space, right? In the probability space. So if you know the old fuzzy logic, T-norms and all of that stuff, you can say that person implies proper noun can be converted into something like probability of a person is less than equal to probability of a proper noun. Just imagine that makes sense. If I am 1/3 person, then I should be at least 1/3 proper noun, maybe more, right? That kind of stuff. Similarly, probability of time will be less than equal to the sum of the probabilities of the various part of speeches. That makes sense, right? So now what have I done? And I can now write it in the form a constraint less than equal to 0. So essentially what have I done? I have taken an initial constraint that my domain designer gave and have converted it into a constraint in the probability space, which is actually being output by the neural model. So this probability of a person is parameterized by theta, the parameters of the neural model. Now I might be able to use these constraints and backpropagate this back to the neural model. So that's pretty amazing. So the general form is minimize my loss function. What is my loss function? Cross entropy or whatever it is that you want to work with, such that there are certain constraints which should be less than equal to 0. Because here I have noted this down as a constraint less than equal to 0 format. And constraint less than equal to 0 is equal to hinge loss over the constraint equal to 0. Why? Because if it's greater than 0, it's positive. If it is less than 0, it's 0, right? So that's exactly the form. So it's minimize the loss subject to the hinge of the constraint equal to 0. And whenever you have this constraint optimization problem, there are multiple ways to solve it, but one such way to solve it is using Lagrangian relaxation. So you iterate over updating weights and Lagrange variables, right? So we'll call this hinge of the constraint as hk of w for kth constraint. So my problem is minimize the loss function subject to hk of w equal to 0. And then we can convert it into a Lagrangian, which is loss plus lambda k hk as my loss function. And that's it. We can then apply the theory of Lagrangian to actually optimize this. By the way, very interesting thing that I will share is that suppose I don't give you training data. I have semi-supervised data, which has supervised and unsupervised part. This hk of w is actually internal consistency property, right? That if you are proper noun, you should have probability greater than that for person and things like that. This has nothing to do with the goal labels. So you can actually impose the second part of this loss function on all of your unsupervised data. So for semi-supervised learning, you can also create a loss which is unsupervised, which is that make sure that my constraints are honored. Whatever you output, make sure your constraints are honored, right? So that gives you another handle to use unlabeled data very well. Okay, so what is my algorithm then? My algorithm is something like, okay, optimize cross entropy first for some warm-up phase. So you have got some initial deep learning parameters, W, and then you look at which constraints are not satisfied in my data. And if some constraints are not satisfied in your data, increase those Lagrange variables, increase those lambdas. After that, again, do some deep learning with new loss function, repeat this process, and there is some theory which says that the number of times you repeat the training should keep increasing and the learning rate should keep decreasing for it to converge. The theory is not very important. And at some point you stop and you say, okay, I have gotten a good enough model. This model has now learned to satisfy the constraints and also optimize the cross entropy. And so you take the model out from the middle whenever you stop. This has given you a neural model which is constraint aware. So now let us see how it does. So this is the task of NERPOS. On the x-axis, so y equal to 0 line, I show you the result. So I normalize it. I show you the result for no constraints at all at training time. So this is like a pure neural model, pure data-driven, right? So modern AI is data-driven, but it doesn't have to be completely data-driven, right? So the red is pure data-driven. That's 0 at the moment. Suppose I do constrained inference, right? That is the yellow line. It does better. You get some improvement in the F1 score. If you do constrained learning, you get even further improvement in the F1 score. So that tells you that getting the neural model to be constraint aware gives you more bang for the buck. And then if you have unsupervised data, then you can use all that unsupervised data, without any additional effort, and that gives you even more improvement, which is not surprising at all, right? So if you have very small amount of training data, being able to use a lot of unlabeled data meaningfully will give you a lot of improvement. The other interesting thing is that if I had to do constrained inference, then I have to run some complicated inference procedure, and that inference procedure will take time. So in this particular case, our test time became about 3,000 seconds for constrained inference, whereas if you're doing constrained training, then at test time, I just have to still do a forward pass. I can now forget my constraints, and that gives me a much faster, more than an order of magnitude faster test time. This will be equivalent to no constraints test time, but then their performance is low. So therefore, what ends up happening is that constraint learning gives you the best balance of test time, inference time plus performance. I'll give you some more results. So, this is the work we did, 4 years back. We published it in Neurips. We started moving on. And then another PhD, by the way, and in here, there are some other results, like in this paper, Yatin had worked on fine-grained entity typing. And again, on the various y-axis, this is the amount of training data. And the second, last 3 columns is the number of constraint violations. So you can see that your baseline has a weaker performance and huge number of constraint violations. Whereas my constraint learning not only has better performance overall, but it has far fewer number of constraint violations. So it's actually honoring the common sense that the human is providing as domain insight. Now, the story goes that, Yatin did this work, moved on to something else. On the other hand, Keshav, my PhD student, was working on open information extraction, a common problem that, people relate me with in the field of NLP. And he looked at the model output and said, oh, my extractions are not covering various words in the sentence. I want the recall to improve by covering more words in the sentence. Now, that was his insight. And how did we model that insight? Typically, in a neural model, it's very hard to model these insights because we don't know what the model is doing. But in this case, the system decided, Keshav decided, let me pose this coverage as a constraint. So he came up with 3-4 simple constraints. He added those constraints to the neural model, and within a very limited amount of effort, he got a fair amount of improvement. In a very different context, Tanishk, an undergrad student, master's student, was looking at extraction from tables, nothing to do with anything that we have studied so far, from research papers, from material science. And he realized that these tables have this characteristic that then there is percentages of in a composition of materials, and these percentages should sum to 100. Or if a column is material, then the composition should be a row, and things like that. There are some constraints, consistency constraints within a table itself, and he modeled them as constraints. And again, he found significant improvement, went from 78 to 84. And so bottom line is, we have ourselves found a lot of success in the following way. We train a neural model, forget about anything, we train a neural model, we then analyze the output of the model. We realize that the model is making these kinds of mistakes. We find those kinds of mistakes, cast them as a constraint. This is a way to get human insight into the model. And in low data settings, we find that generally improves performance tremendously. Also, we can start to get some guarantees in the sense that if we keep increasing the lambda variables, eventually we are guaranteed to get a neural model that will satisfy all constraints. So if we have a safety critical application, if you really want to send a satellite to Mars, or if you want to really get the injection, and if you want to use the neural model for those kinds of decision-making problems, we might be able to honor the safety as a constraint as part of the neural model. And last but not the least, if we have a lot of unsupervised data, we can use the constraint loss as consistency regularization for the model. Okay, we can talk more about this, but in the spirit of moving forward, let me get to the next piece. Okay, and the way you can compare the previous piece with the next piece is that in the previous piece, the constraints are very simple. These were like simple inequalities, simple, right? This implies that. But now I'm going to get into more complicated reasoning problems. So by the way, both of these are perceptual reasoning problems. Perception was reading the text, and reasoning was honoring the constraints. In this new case, we will realize that my reasoning is so complicated that it's a bad idea to ask the neural model to honor the constraints. Rather, I should use a symbolic algorithm to actually honor the constraints. Okay? And this we will study in the context of visual Sudoku. Okay, so what is a visual Sudoku problem? I give you a partially filled Sudoku's image as input, and I want the final model to output a fully filled correct Sudoku. That's the goal. And now you can start to see what's going on. This is a problem where, first of all, we need to understand what's going on with the image. That's a perception problem. And we know that deep learning networks are really good at perception. Of course, we still need to learn the weights. In an ideal world, the way I would want to solve this is that I would want to create a symbolic Sudoku partially filled in the middle, and then give it to a symbolic reasoner, right? Some symbolic reasoner which is really good at reasoning. We know that symbolic solvers are very good at reasoning. But we'll work on this inner setting where I am not giving you the explicit constraints. You have to learn them from the data. And moreover, I am not even giving you this intermediate output. Okay, so this is the interesting setting, because if I give you this intermediate output, then you can decouple the perception and the reasoning. You can say, oh, perception will be trained separately and the reasoning will be trained separately. But we don't want to do that. We want to solve them in an end-to-end system without giving you the intermediate output. And if I do this, then I have a problem, because now what is the benefit? The benefit is that now we will have an explicit representation of symbolic constraints in the language of the symbolic solver. So we have some interpretability, but the challenge is that we don't have the intermediate supervision. So we somehow need to backpropagate through the symbolic reasoner. Okay. Building it one step further, we will assume that our symbolic reasoner is an integer linear program. Integer linear programs can handle all NP-hard problems, so that's not bad. And we can say that the parameters of an integer linear program are A, B, and C, where we want to minimize C transpose Z. Z is the variable, C is the parameters, such that some linear constraints A, Z plus B greater than or equal to 0, and Z's are in my integer space. Now, in the forward pass, I will take my image using the deep network with parameter S by theta, which will output A, B, and C. The neural model will output the ILP. So this is programming in one way. This is a specific kind of programming where the program is an integer linear program. It will output A, B, and C, which will create an ILP. Then the ILP will solve itself using an ILP solver, and that will give me the output. Okay, so that's my forward pass. So the forward pass is not simply do a simple neural forward pass. It is neural forward pass followed by a symbolic algorithm. The backward forward pass, you need to define derivatives with respect to A, B, and C, which is a hard problem because it goes through a symbolic algorithm. Now, good news is somebody already did that for us. So these folks at ICML 21 came up with a method with complicated math in it, where they can backpropagate through an ILP. Pretty amazing stuff. Encourage you to look at it. However, it doesn't work in practice. Now, why doesn't it work? It doesn't work because, I hope you know, in machine learning, inference is always a subroutine of learning, right? You first do inference, you match the output, you create the loss, you backpropagate. So inference is always the subroutine of learning. And that means that I need to call an ILP solver for every training data point in every mini batch. It's just never going to scale. So we cannot practically use these algorithms because even though they work in theory, in practice, they will never scale. So in this work, again work by Yatin, we were able to create a solver-free framework for learning in these neural ILP architectures. So the first thing I will say that I really like this neural ILP architecture itself, perception, reasoning, neural ILP. But to make this work, we need to somehow backpropagate without running an ILP at training time. And here is the nugget of the insight, okay? The nugget of the insight is that my linear constraints, each linear constraint in an ILP can be thought of as a binary classifier, which is separating the positives, the gold targets, the solved Sudokus, from the negatives, the random Sudokus, the Sudokus that don't quite work, okay? Let's look at an example. So visually, just to get the intuitions going. So let's say these are all my integer solutions. And let's say I have 4 learnable constraints. So when I look at these 4 learnable constraints, each constraint sort of separates some points from the others. And in fact, the points that honor all the constraints are the feasible set of an integer linear program. Moreover, you have an objective function. Let's say C transpose Z, which also is a line. And as you keep minimizing it, as you keep going in some direction, at some point you will hit the last feasible point. And that would be your final solution. So this blue dot would be your final solution. Okay. Now, if you think of each constraint is honored by some points and not honored by some points. And the true answer has to honor every constraint. So whenever there is a point which does not honor a constraint, that means it is not a solution, right? So that's my intuition. So it's sort of each constraint can be seen as a classifier separating positive points from the negative points, right? So if, for example, if I have this constraint, then all these points can be the correct answers, but these can't be the correct answers. These are the negatives. If I have another constraint, then I get rid of some other negative points. And I keep doing this, and you will see that the points that remain will be the ones which will be somewhat in the feasible set, right? So intuitively, a good point, a correct point should honor every constraint, and an incorrect point, a negative point, should violate at least one constraint. Okay. So we keep adding constraints, and then we are left with the feasible set. But the feasible set may have many points still. And so there is a trick, and I'll skip the intuition of the trick too much right now, but basically we can put together one more constraint, exactly one more constraint, which is C transpose Z less than or equal to C transpose Y star, if we know the training example Y star, the correct answer, which basically says that, look, my value of the objective function cannot be lower than the value of the objective function at the correct point, right? So that adds a final n plus 1th constraint, and after that, all the other points are now in the infeasible set, and only one point is in the feasible region. I guess the colors are not showing very well, but this is gray at this point. This is my feasible region, this triangle, and only one point satisfies it. So now my ILP, instead of going from argmin C transpose Z subject to AZ plus B greater than or equal to 0, becomes argmin 1, because it's now a constraint satisfaction problem. There's exactly one point that satisfies it, subject to AZ plus B greater than or equal to 0 and C transpose Z less than or equal to C transpose Y star. Okay. If you didn't get that, it's not critical, right? What is critical is that if I give you the correct answer at training time, your job is to learn constraints such that only this point honors all constraints and all other points violate at least one constraint. That's sort of the intuition. Okay. So my loss function that I consider, that I build, has to encourage each positive example to satisfy each constraint and each negative example to fail on some constraint. And how do I get negative examples? I can have various kinds of negative samplings, sample in the neighborhood of Y star, use positive examples from other batches, examples in the batch as negative examples, etc., etc. And when we did this, we found that our method just blows away everything else. First of all, notice that this is a neurosymbolic problem. It has image and it has symbolic reasoning. You cannot solve it purely by symbolic methods because they can't do a good job on the perception. You can try to solve it purely by neural methods, which is this top one, which is the state of the art. It has accuracy of 71 on this data set. There are other methods like SatNet, which have worse accuracy. There is the COMBOPNet, which we were inspired by, and it has basically no accuracy because it can't train at the scale. And we get hugely improved performance and much less training time. Of course, notice that the test time is going to be higher because I'm solving an ILP, right? Similarly, we worked on textual knapsack, where the knapsack is another NP-hard problem, and you find that you write the knapsack description in text, the perception is dealing with text, and knapsack is kind of solving it, the ILP is solving the knapsack problem. And again, we find that as the number of items increase, our performance is vastly better than the competitor because it can't scale. So let me share with you sort of the take home here. So the first important take home is that, interestingly, symbolic representations can be outputted by a neural model without any intermediate supervision. To me, that was very interesting. You can train a model end to end. The neural model can output the code, ILP in this case, completely without supervision. That's amazing. Second, symbolic algorithms can be explicitly used at test time in this end-to-end trained fashion, and this would be especially useful for when you have complex reasoning with perception. The other nice way to look at this is the system 1, system 2 analogy. So the system 1, I hope you know this, Kahneman's story, the system 1 is intuitive, system 2 is deliberative. So system 1 is sort of intuitively figuring out what's the ILP, and then the system 2 is doing this reasoning in a more deliberative fashion, solving the ILP to get me the correct answer. Okay, there are more interesting implications, but I'll move on. So Pushpak, how much more time should I take? 10 minutes. Okay, so good. So that gives me some time to talk about the third piece here. And the third piece is a little bit more sort of far in the future, but we'll see. Here, A human is giving you the model. The human has a symbolic theory, and the neural model is working on that symbolic theory. So we are switching things around. We are saying that there is a complicated symbolic theory, and this really goes back to the good old-fashioned AI. I don't know how much of you know this term GoFi, right? GoFi is the good old-fashioned AI where there is some logical theory that is generally being provided by a domain designer, like a satisfiability problem, a planning problem, or probabilistic theory like a weighted maxsat problem or a probabilistic planning problem. And my job is to solve that problem. Right. Now, solving that problem is always possible, but these methods are at least NP hard. They start getting into Sharp-P, they start getting into X time, so they don't really scale in the symbolic world. The neural models are intuitive. So can we use the intuition of the neural model to solve these sort of more complicated first order reasoning problems? And the intuition that we are going to bring in is that can I train on small training data points and test on large training data points? That's the intuition that I'm going to bring in. Okay. And we will do this in the context of probabilistic planning. So just some jargon to, so that we are all on the same page. I hope everybody knows what a Markov decision process is. It has states, actions, transition function, reward function, some horizon, sometimes an initial state and a discount factor. What these are is not critically important, but you have an agent which can take an action in the environment. The environment gives it the next state and a reward, and the agent's job is to find a policy, learn a policy pi, which is a function of the state to action, that maximizes the expected long-term reward, right? So all of AI often is modeled as a Markov decision process or its extensions. Now let us work in an object-centric world, first-order world. So instead of states, we will drill it down to say there are classes of objects, there are state predicates, and then there is transition function and reward function also mentioned in the first-order form. So everything that you have in an MDP can be converted from an RMDP into an MDP. So I think of MDP as a ground phenomenon, RMDP is a first order phenomenon, right? And I'll give you an example very soon. So we will split it into two parts. The first part is the domain description. Think about a domain which can have varying number of objects, right? So what will be part of the domain? Classes of objects, state predicates, action predicates, transition functions, and so on. What's part of my domain? A specific domain, the specific objects that are in my domain, the specific initial state. So let's give an example. So let's say I'm in this toy world where there is a grid, okay, XY axis, there is an agent, agent has tools, agent may have to navigate to pick up tools, the tools may operate on items, so agent has to navigate to the item, then it gets some reward, that kind of a world. Then you can have some fluents, state fluents, which basically say, okay, agent is at which location, which tool is damaged, which, etc. There may be some non-fluents like what's my grid structure, things that do not change in my domain. Then there may be some action predicates like go up, the agent has to go up, repair, this agent has to repair this tool, and things like that, right? Now, if I have a 2x2 grid with one item and one agent and one, other things, you can easily write it as this instance description by saying, okay, there are two x coordinates, two y coordinates, two tools, one item, one agent. But on the other hand, if I have a bigger domain, I can simply make small changes in my instance description because all the general properties of the domain are described in the domain itself. So you have 2x coordinates, 3y coordinates, two tools, etc., right? So now you can see that this kind of a representation allows you to represent an infinite number of problem instances. I can just add new objects and it creates a larger domain. But there is something similar about all these domain instances because they're all following the same dynamics, they're all optimizing the same reward. So you can hope that there is some general principle about that domain that you want to learn. Let's say, you have seen the Tower of Hanoi problem. If I give you a Tower of Hanoi problem for 3 blocks, or 4 blocks, or 5 blocks, or 10 blocks, or 100 blocks, intuitively, there is some general thing about Tower of Hanoi that you can learn with small examples. And then if you really have to solve a 10 Tower of Hanoi problem, it will take you time, but you know the principle. You know what to do. You know how to create an n-1 block. You can come up with the recursion in your mind and actually play it out. So the question is, can my neural model learn the same? Can my neural model learn from small instances of a problem, learn something general about the domain, and then when it is tested for a large instance, just apply that policy that it has learned and solve the larger problem? That's the vision here. Okay, the vision is very interesting. And interestingly, the original vision is not ours. It comes from way back in 1999 by a seminal paper from Craig Boutillier, who is currently at Google, I think, from 19, right? I said 99, and they called it relational MDPs. It actually, there was a theme going on in those days, 20 years ago, the theme of statistical relational learning. So a lot of probabilistic relational models, Markov logic networks, lots of things came out at that time, okay? From this came in the context of reinforcement learning and planning. And there were several papers written about this until 2010s, but none of them really worked. So they were value iteration, first order version, policy iteration, first order version, some machine learning based approaches, but the machine learning based approaches would use approximations using linear basis functions, which was what was prevalent at the time. So the vision was broadly unsuccessful. Maybe it was too ahead of its times. And one of my friends often said that anything that you do today has been thought about 20 years ago. It's just that they didn't have the tools to do it then. You have better tools, you can do better. And maybe you will reach a certain point and 20 years ago, somebody else will take up. So don't worry if your papers are not getting citations. They may be too ahead of their times. So that's a nice thing I always remember when I don't get citations. So, so this was our time to come back and start looking at it, because now we have much better machine learning methods, okay? So what is our goal? Our goal is that I give you the domain description, I give you small training problems. And I want you to learn maybe a neural policy from these training data points, training domains, such that it can now apply out of the box for a much larger domain at test time. You can call it zero-shot transfer if you want. You can call it transfer learning. You can call it size invariant learning. You can go, it goes by many names. But it's easier said than done. There are too many challenges here. And one of the challenges is that the state is symbolic. It is in the first order logic, then logical predicates, objects, this, that, and the other. Two, the state space is variable across domains of different size. Because if I have 2 objects, then maybe I have 10 state variables. If I have 3 objects, maybe I have 15 state variables, and your state space becomes 2 to the 10, 2 to the 15, and so on and so forth. In fact, your number of actions is also different, because I may apply the up action on all the grid cells, and if I have 4 grid cells, that means 4 actions, and if I have 10 grid cells, that means 10 actions. So whatever I need to do it in a size invariant or number of object invariant way, looking at the domain description and the general first order properties. Now, in the interest of time, I'm going to skip how we do it, which is really clever in some ways, but it requires certain, detailed discussion. But I'll give you the main intuitions. So the main intuition is that we convert our domain or instance into a graph. And the node is any object tuple that shows up as an argument to a state variable. And then all the objects. And then we think about, which should, what edges should connect. So if one state variable changes the other state variable, then their corresponding object tuples will have edges, etc. And then we define some features for each node, and each feature sort of represents what state variables are true or false in the given state, which are relevant to this node. And so essentially what we do is we take an RDDL instance, or forget RDDL, we take this planning instance and convert them into graphs. Now, why graphs? What's so special about graphs? Well, graphs and graph neural networks, therefore, are able to run on variable sized graphs. They have shared parameters. Just like RNN and LSTM can run on sentences of different sizes, graph neural networks can run on graphs of different sizes because they have shared parameters. So we benefit from that theory. Then we have to also think about how to get a policy, because now we have done encoding. How do we do decoding? Number of actions is different. So again, we figure out after running graph neural network that we have to do some action decoders, again, which are in the first order world. So again, I will skip, but basically, if an action is applied on a particular state variable or on a particular object sequence, then I will take embeddings of these objects to define what is the value of that particular action. And then again, it will have shared parameters. So I'll skip some of these, and that will finally give me the policy. So this is our complete sort of high-level solution space. The initial instance gets converted to a graph with nodes, edges, and features. We run a graph neural network on top of it, message passing to create embeddings. We pool those embeddings to create state embeddings. We create action decoders, which are also instantiated with shared parameters based on the action predicates. And that will be applied again and again based on the number of objects to give me a policy, and then I can normalize to get a probability distribution over the actions. When I do this, then I allow myself to train on small problems of a domain and then test on large problems of the domain or even much larger problems of the domain. And here we use an imitation learning framework, but we can also use a reinforcement learning framework. And we compare against something which is not even a fair comparison, because there's something called offline planning, there's something called online planning. Prost is an online planner, SimNet is an offline planner. They don't compare with each other. So this is just some sort of high-level illustrative differences. Otherwise, our method is sort of unique in that it's an offline planner for training on small and testing on large instances of the planning problems. And here 0 means random policy, 1 means the best policy known so far. All the various TT, CT, etc. are domains. And what we find is that, first of all, we are much better than random. That's good news, right? There is zero-shot transfer, an interesting zero-shot transfer happening. Second, we are sometimes better than our teacher. So Prost is our teacher at training time, and notice that for some domains we do much better, because Prost does tree search and it sort of can't scale. For large domains, we can scale easily because we are just doing a forward pass. And if we start doing much larger problems, then our differences between Prost and SimNet start to reduce. So we hope that when you get to 20, like even bigger problems, 100 grid size and 1,000 grid size, then this would be even more scalable. So in this case, we have been able to solve an original symbolic problem where the inference time was uninteractable because it was NP hard and so on, and approximations didn't work, in a kind of an intuitive fashion by training on a small instance of a problem and testing on large. This we did for planning, but we also did it for constraint satisfaction. So for example, if we want to go learn Sudoku, but we want to learn Sudoku in a size invariant fashion, like we train on 9x9 Sudoku and test on 16x16 Sudoku, we have been able to even achieve that. So we can actually use neurosymbolic AI for model-based reasoning, good old-fashioned AI. We have now solutions for first-order problems, which the vision of whom is really, really amazing for AI, really amazing for building intelligence. Tasks will have to be represented in first-order language, but now the neural model can train on small and apply out of the box on large instances. So I think I'm out of time also. So let me now just wrap up with one final slide. So this is what we touched on today. And just taking a step back, I have shown you various instances where neurosymbolic AI is useful in a low data setting. Nobody ever said that I have too much training data. Unless you are OpenAI or maybe Google, you don't have enough training data. What do? You pay people some money, you request your friends to annotate some data for you, you do crowdsourcing. You will still have 100,000, 2,000, 10,000 instances of data. If you want the maximum bang for your buck, get the human insight, put in the constraints, do constraint learning, and you will find that neurosymbolic AI actually gives you better results. It'll be faster in inference with complex constraints, but if you have with less complex constraints, but if you have complex constraints, then you want to use symbolic algorithms, because then you can start getting some good performance out. You will start out guaranteeing some output constraints, you will enforce consistency, and then you can actually do size invariant learning, which is something I mentioned towards the end. And what I did not mention, some other aspects, is that if you have to retrieve knowledge, you still need neurosymbolic AI. If you have to do explanations, you need neurosymbolic AI. There are many, many other cases where you need neurosymbolic AI, because the strengths and weaknesses are complementary in many ways. So the jury is out. Who wins? Whether it is Yoshua Bengio or whether it is Henry Kautz. I don't know if you know this difference, but Yoshua Bengio believes that there should be neurosymbolic AI, but the symbolic AI should also be done by neural. This is Yoshua Bengio's vision. He says that it is very important to get all the skills that symbolic AI has, but the method to achieve that has to be completely neural. Whereas there are a lot of us from more traditional AI who believe that let symbolic AI do what it is good at, let neural AI do what it is good at, and let's build bridges. And let's see who wins in the long run. It's a very, very interesting place to be. And I will stop here. I should also thank all the funding agencies which supported this work. Thank you very much.
We have some time for questions.
Sure. Thanks.
Questions?
Yeah, thanks, Mausam. Very nice and visionary talk. One question about the first work on the constraints, just practical consideration. Is it possible to have like a priority order of constraints? Like certain constraints I cannot violate, so kind of let those come in the inference and then others in the training, or
Very interesting question. So the question is, what if some constraints are really hard constraints, some constraints are soft constraints? Maybe that's the way you can think about it. So first of all, we talked about hard constraints, but if you have soft constraints, it's very easy to work with them also. It's just that you have to just stop the Lagrange variables to keep increasing at some point. See, because you will have some constraint violations, you will increase the Lagrange variables. You can play with the Lagrange variables on when to increase and how much to increase. For example, if a constraint is a hard constraint, you increase them with a higher learning rate. If it's a soft constraint, you increase them slower. You can also choose to find the right lambda with the dev set if it's a soft constraint. That way you don't have to keep the Lagrange variables going. You can just do hyperparameter search over the lambdas and figure out, with the dev set, which gives you the best performance. So actually in some of the follow-up work where I showed you that it showed up in a different case, we did not impose them as hard constraints. We simply imposed them as soft constraints and got the lambda to be tuned using the dev set, and that worked for us. If you have a combination of hard and soft, you can do the Lagrange for one and the hyperparameter tuning for the other, and things like that. Or you can insist that lambda for hard is much higher than lambda for soft, or things like that, and that might just get you to achieve what you want to achieve. Yeah.
Hello. Thank you so much, sir. This was a very insightful session. Sir, I believe that this is a core topic and it would have a diverse application over many domains. Could you, sir, suggest or has it been applied in the medical domain so far, or is it still an open challenge?
Good question. And let me think about. So medical domain itself can get into very different machine learning problems. So there are electronic medical records where you may want to have some consistency between, what was the symptom and what is the disease prediction and things like that. There's also vision tasks where you can think about, okay, where is the tissue, where is the organ, am I segmenting right, and things like that. So I will abstract out from that. I have to really check whether they have been explicitly used in medical diagnosis kind of settings. But I would say that in vision, they have been applied. And one particular example is, and this is very interesting, suppose I want to segment a human face or whatever. Let's say my prior or my constraint is that each human face should have 2 eyes, 1 nose, 1 mouth. Now it is very easy for me to say that they should have 2 eyes, 1 nose, and 1 mouth, or 1 lips, whatever. How does the model figure this out? Now the model needs to automatically create eye segmenters. It needs to learn these eye segmenters and then additionally honor the constraints. So the eye segmenters become some kind of an implicit neural models. And the output of the implicit neural models should have some consistency property with respect to the final prediction. Those kind of ideas have been considered. It is possible that similar ideas can be applied to medical diagnosis, like say in the radiology setting, where you say that, okay, there should be at least 1 villi and at least 1, crypt, and at least 1, or there should be at least 1 this kind of cell and 1 that kind of cell. And those predictions are also implicitly part of the neural model. It is quite possible that some things can be done. I'm not entirely sure whether they have been done, but given the fact that this literature is evolving very fast, I would encourage you to look at some of the surveys that have come out on neurosymbolic AI in the last year and a half. You might find that people have considered.
In the final application of training on small test data and then applying it, learning something general about it and applying it to larger test data, this reminded me of how the bread and butter algorithms of data such as algorithms such as Dijkstra for graph algorithms or KMP for swing algorithms. Could this technique be applied to searching good algorithms for these standard problems that we haven't somebody hasn't come up with yet?
So 2 or 3 questions. So first of all, and a very interesting question. Now let's first differentiate between Dijkstra's and the way we are working in the world, right? The Dijkstra's algorithm came from Dijkstra's. There was no learning whatsoever, no parameters. The algorithm will work on small graphs, will work on large graphs, right? So that's the first thing to realize, that there is a distinction. Another interesting question which you did not ask That question is, well, what if I give you Dijkstra's algorithm? Can neural model work with Dijkstra's algorithm in the first place? And I believe the answer to those questions is starting to be yes, right? So just the way the neural model can output an ILP, which then gets applied to an ILP with an ILP solver to get the final answer, you can get the neural model to output a graph, which then on top of which a Dijkstra's algorithm is applied to give you the correct answer. So I think that's where a lot of interesting research can be done by saying, okay, I have a shortest path problem, but my input is a visual input. Can I convert this visual input into a graph automatically such that the Dijkstra's algorithm gives me the same path that I was getting from my original image? So that's another thing we can do. But the question you raise is still the third question. The question is, maybe Dijkstra's is not a very good algorithm. Maybe there's another algorithm that is lurking somewhere, which we don't know because we didn't have Dijkstra's 2.0. Somebody else, like a neural model, comes in and actually learns from data to create an algorithm. I think that's a very interesting question. Now, there is a limited success I have heard on matrix multiplication. Some of you may have seen that one matrix multiplication or something was reduced, which was a major development in the last 20, 30 years by a neural model. So I think very small instances of that are starting to show up, where a neural model is improving on existing known algorithms by small benefits. But I haven't seen like a breakthrough, like a major thing yet. But I think that's a very interesting question, and you should work on it. If you want to work on it, send me an email. So, yes.
Hello, sir. I have one question regarding the training. So, if it's I have some constraint today, and I've already trained a model. After a few weeks, additional constraint comes up. So, is retraining necessary, or we can keep adding those constraints as and when they keeps coming?
So let's think about this, right? So the constraints were present even in original training data, but we didn't know them. Whereas the data has changed and new constraints have come in. Okay, so those are two different settings, right? So let's look at the first setting. In the first setting, you didn't have a training, you didn't think of that constraint, but you thought of that constraint later. I have a feeling that you should be able to fine tune your model with that new constraint to get even better. You can always do constraint inference. Your original neural model is still valid. You can always apply the new constraint at inference time. So the choice is yours. You can either put in that constraint at training time, do a little bit of fine tuning to make your model constraint aware, or you can apply that constraint at inference time, depending upon whatever is your fancy. Now, if a new constraint has come up now, that's a domain shift problem. That's a transfer setting. That constraint was not true in the training data. It is true in the new domain. I don't think people have studied that particular instance of the problem. And there can be easy baselines, which I can think of the top of my head, like you have a small amount of target training data, you do some fine tuning or things like that. But maybe there is something interesting to be done using some of the known ideas from transfer learning to say, okay, if I have to do constraint transfer, how do I do that? I don't know the answer to that. Very interesting question.
Thank you, sir.
As well as whether you are considering human in the loop learning also to understand the constraints and give them incremental.
So all the understanding of the constraints is human in the loop. Because where do constraints come from? In that particular example, the constraints come from the human designer. In fact, to me, I really like it because now human designers can do something. Otherwise, what were you doing? Hyperparameter tuning, increase the number of layers, blah, 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 right? So at least we can do something more interesting. So we always, in practice, will apply a baseline model, neural model. It'll give us good results, but it'll make mistakes. We will analyze the mistakes, everything we used to do in the old times. And then the only step is that, we'll analyze these mistakes and convert the mistakes into a constraint or two, and then give it to the neural model and repeat. So it was always human in the loop. The drift question I've already answered, yeah, to the best. I don't have a good answer there, yes.
So the second criteria that you said, so you're learning the ILP constraints. So firstly, like suppose if you don't know how many constraints you should have, so how to tackle in that, and supposedly you are applying the problem in the in the first category, and you don't want to specifically mention the constraints like in the OpenAI, but you want the neural system to learn the some constraints. So is
Yeah,
that
those
possible?
are both very good questions. So first of all, whenever we show some, give some talks, there's always too many details which we are sort of sweeping under the rug. So you're asking about one such detail. How do we figure out the number of constraints in the ILP? And we don't have an answer, right? So that is just like a max number that we have set based on the amount of GPU memory available to us and what we think the data might need, blah, 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 right? So this is just the first demonstration. So basically, right now we have a max number of constraints. I forget, 64, 700, 800, whatever, some number of constraints, and we are learning those constraints, right? The good news is that 2 constraints can always be the same. So as long as your number of constraints is a little bit higher than what you might need in your domain, this will work out. But if your number of constraints is smaller than what you might need, you might find that your training never succeeds because it leads to infeasibility. You can never find the constraints that are only honored by the positive points and never honored by the negative points. So you will be in either one situation where lots of negatives become positive, which is bad, or in a situation where you cannot learn the constraints are only positive, right? Separate. So that you can't separate. So that that's a question. It becomes more of a question when you want to do this in a size invariant fashion. So notice I have touched on various things, but it's not one problem where I have shown you from beginning to end, right? Why? Because we are currently working on a neural ILP architecture for size invariant learning. But now my number of constraints is dictated by the size of the problem. If I have a small problem, I have small number of constraints. If I have a larger problem, I have a larger number of constraints. So I need to provide this flexibility to the mechanism to say, if I give you a small problem, learn small number of constraints. If I give a large problem, large number of constraints. So that is something that we don't have a very smart answer to. The second question you asked, sorry, I forget. You had another, what was your question though?
If you don't know the constraints, can you ask the model?
Right. So the other thing is constraint learning. Okay, so very good. So first of all, you should also ask yourself, why should we give constraints in the first place? Now, this is a slightly longer answer, but hopefully it will be informative. Why should we give constraints? Because the data already honors the constraints. If the data honors the constraints, why should my neural model also not honor the constraints? So there are two things to learn here. First of all, it's a low data setting. Because it's a low data setting, not everything can be learned. Secondly, and believe it or not, constraints give you something a little bit more than what my data gives you. Why? Because data only gives me the final gold answer, whereas constraints is on the probabilities. So that means I am able to say that if you are 1/3 person, then you should be more than 1/3 proper noun, even though the gold answer is neither person nor proper noun. Okay, so you are actually regularizing the model even for smaller probabilities. It's a stronger regularization, and therefore the model works well. That's the first thing you have to realize. The second thing that you have to realize is that if I give you a huge amount of data, generally the model will work okay. So you may not find as much benefit of adding constraints in a large data setting. That's the second thing to realize. The third thing here that we need to realize is that when I give you small amount of data, learning constraints is some kind of a bias that you are adding to the model. So you had a generic model which was less biased. It had many local optima, and in low data setting, it did not get to a good local optima. If I give you constraints, I am regularizing it. If I don't give you constraints, if I ask you to learn the constraints, and then honor these constraints at training time, with the small amount of data, I'm asking you to do too many things at the same time. So now it is not entirely clear whether it is actually reducing the bias or asking you to learn more things. It is possible, increasing bias or asking you to learn more things. It is possible that it can be done, but my hunch is that we can do it better if we had too much data. But if we have too much data, then we don't need constraints in the first place, and so on and so forth. So it's not entirely clear whether learning of constraints is going to be helpful in a low data setting. But again, I think that's an interesting research question.
Yeah, thanks, Mausam, for interesting talk. Since I'm working more on the system side, so my question is like, now looks like the neurosymbolic AI has mix of traditional linear algebra plus our control flow kind of, workflow which we'll have. So what do you think this accelerator community, all the people are moving towards building accelerator, which are primarily for the matrix multiplication and stuff like that. So what's your message for that community, how they should look into it, the neurosymbolic AI?
I would, first of all, I should warn you, I have zero idea about the hardware side of things, right? So thankfully, I have smart students. So that's how, things get done. If you want me to write code, I can't write it to save my life today. But nevertheless, thinking from first principles, I think a lot of hardware acceleration was sort of a consequence of what was coming into the world, right? LSTMs came in, became important. The hardware community said, let's put LSTMs into the hardware one way or the other, right? Transformers came, had too many connections. They said, okay, let's put in some specialized hardware for transformers. The hardware community today is not, I don't know, I can't say that, but one part of hardware community is sort of responding to the developments in machine learning, right? So I would say that let us wait for neurosymbolic AI to be successful. Once it gets successful, once we find really clear application areas where this is really needed, we will also know what architectures are needed. It could be neural followed by symbolic. It could be symbolic with a neural, API call. It could be a tighter interplay. We may have to think about maybe a stronger interaction between a GPU and a CPU. I mean, those are the kinds of questions we'll have to study. But should we be studying them today? I don't know. We are still building neurosymbolic AI, in my opinion. So maybe we should wait a couple of years.
Okay, last part.
Yeah. Thank you, sir, for the interesting talk. So actually, I work in the fairness area and all, and like nowadays, lots of talk is going upon like these ML models like gives biased output or unfair output, especially in the recommendation and all. So like I was just like whenever you were saying like imposing the constraints and then enforcing those things. So I was just like thinking like whether like imposing those constraints there in the recommendation learning process and all, and just to make them fair and like
Oh,
all those
absolutely.
stuffs are
Absolutely. And people have been doing this. So just so you know. So in fact, if you look at the fairness literature, some of the early works actually say that let's put in a fairness constraint as an auxiliary loss. So if you think about what is a constraint, if you're talking about simple constraints, we are finally adding them as auxiliary losses and then increasing their importance using Lagrangian. So I think the same can be easily done in the world of fairness. You have a fairness loss, you put the fairness loss as an auxiliary loss, and then you sometimes increase its importance if the data requires you to do
yeah.
that.
And like other question is regarding like if we just add those constraints, so what is the like increase in the parameter of the model to get learn, like is it like still getting too high, or like what's the...
No, so the original size of the model is not increasing by much.
Okay.
But the original size themselves are generally high, right?
Yeah.
Because the neural models are, large models. So typically, what are the new parameters we are adding? Some lambda variables for each constraint. That's a 10, 20, 50, 100, however number constraints. So we are not adding many parameters. Training becomes slower because there's an alternating minimization, and so there are two sort of minimization, maximization happening. But other than that, the number of parameters is not increasing. Right?
Okay, thank you, sir.
Hi, sir. Very inspiring session today. So my question is, so there are a lot of models coming up and they fail on some very common mistakes. They make very common mistakes. So, and these constraints are basically very intuitive, right? So can we create a metric for basically checking the common sense if they are following the constraints? So can we use this as a metric for checking the common sense of the models?
Yes and no, right? So common sense is a very complicated problem in and of itself. Pushpam can give you lectures on common sense, I'm sure. So the whole point is, if you can model common sense, sure, right? So if you figured out, okay, this is a common sense that it is sort of missing out on, let me add a constraint evaluation metric for it, sure, we can do that. But generally, we have found that when we start writing down common sense, we limit ourselves because there is so much common sense that is implicit in our mind, but once we start making it explicit to the model can only do so much and misses out on everything else. So in practice, if you come from a more NLP or more sort of philosophical AI point of view, you have to learn common sense from data more than you can explicitly provide it. But if there are certain specific things that the model is missing out on, you can always explicitly provide it as constraints. I think that's the best I would say.
Okay, so Mausam, last question is mine.
Okay.
So, what corresponds to variable and variable assignment in neurons, in neural network?
what corresponds to a variable and a variable assignment in a neuron. Okay. Okay. So this is a symbolic view of neural networks, right? So should we need that view? I don't know. But since you are pushing me there, I would say that why isn't a neuron itself a variable, right? And the vector embedding that it has, its variable assignment. Or you can go one step lower and say each dimension and its sort of assignment. But that's not a very interesting view, because that variable by itself may not have an interpretable meaning to us. See, when we think about symbolic methods, we often think about a symbol having a tangible meaning to us as humans. And in a neural network, each individual neuron or a dimension of that neuron may or may not, or often not, have a tangible meaning to us. So if we want to build the bridge, then let us think about, okay, I want to figure out a concept. I create a symbol for it. Then I look for that concept within the neural network. And you will find that there will be a subset of the neural model which will be acting on that behalf. Like some particular neurons will be acting like co-reference modules. Some particular neurons may be acting like the dependency between the verb and the noun and things like that. So those neurons collectively in a certain specific parameter value space will give me the symbol that I'm interested in. So it's still two different worlds for me. And that bridging of the gap, there is no one-to-one or clear correspondence. One neuron may be acting in two different ways, for example, in different parameter steps. So to me, the symbolic view of neural network may not be as exciting unless we start building from the human interpretation and the neural sort of subset. So I don't know if that answers your questions.
So let's try this.
Okay. So I'll have to use the mic. So there is a memento for Mausam, but it's an unusual memento, right? Raj, if you can come and describe what the memento is.
So first of all, thank you so much for such a wonderful talk this morning. Professor Mausam already has this memento in the past event. I mean, it's a tree that we are going to plant for him through 14 Trees organization. So we will reach out to you after the conference and take your consent for it. Thank you so much again. And thank you.
Now I have to invite an extremely important person, Professor Biplab Banerjee. He is with the Faculty of Electrical Engineering and C-Mines in IIT Bombay, and he leads the deep learning-based computer vision research in our institute. And there are two more persons I have to mention. Helping Biplab has been Dhiren from our lab, Computation for Indian Language Technology, and also Atul Kumar from IBM, Raj Sharma you saw just now. They are absolutely great contributors to the conference. The general chairs can sleep because of them. Okay.
Well, thank you, Professor Pushpak, and a warm welcome to IIT Bombay for CODS-COMAD 23. And I'm the local organizing committee co-chair with Manoj Nambiar from TCS Research. So we will have the conference in this auditorium in room number 21 in the second floor, and the posters and the demo presentations will be in the first floor. So all the volunteers, Ankit, Swarnendu, Shivam, all are around, so please talk to them for any kind of assistance. And I hope that you all will have a very academically enriching experience in the next 3 days. Thank you.
It's time for a tree bakery. Next start time will be 11:30. 11:30. We're off by 30 minutes.